Welcome to Math Zone African Motives. Today, we're diving into a powerful application of calculus known as optimization. Optimization is all about finding the best possible outcome in a given situation. It's the process of making something as good or as effective as possible. This means we're often looking for a maximum or minimum value. Think about real-world scenarios. You might want to find the maximum profit a company can make, the minimum distance between two objects, or the maximum volume of a container you can build. The key principle we use is that the first derivative of a function is zero at a maximum or minimum point. The derivative, which measures the slope of the curve, becomes horizontal at these turning points. Looking at this graph, you can see that where the function changes from increasing to decreasing, we have a maximum. The slope, f prime of x, goes from positive to 0 to negative. The opposite happens for a minimum. The slope goes from negative to 0 to positive. So, to find these points, we simply find the first derivative of our function and set it equal to 0. Let's quickly go over the strategy we'll follow. First, read the question carefully to know what you need to maximize or minimize. Second, make a sketch if it helps. Third, allocate variables and write down the main equation. Fourth, if your equation has more than one variable, use extra information from the question to express it in terms of a single variable. This is a crucial step. Fifth, differentiate the single variable function. Sixth, set the derivative to 0 and solve. Finally, use the second derivative test to confirm if it's a maximum or minimum, and then calculate the final answer. The second derivative test is a very useful shortcut. If the first derivative is 0 at a point, you can check the second derivative. If it's negative, you have a maximum. If it's positive, you have a minimum. We call this the second derivative test. These steps are our roadmap. Let's get started with our first example. You will now be able to use the first derivative to find the maximum or minimum value of a quadratic function. Let's begin with a simple example. By the end of this scene, you will be able to set up and solve optimization problems involving two numbers. The sum of two positive integers is 8. Find the integers for which their product is a maximum. Let's break this down using our strategy. Step 1 is to understand the question. We are told the sum of two positive integers, let's call them x and y, is 8, and our goal is to maximize their product. Step 2 is to sketch, but for this problem, it's not really needed. For step 3, we write our objective function. The quantity we want to maximize is the product, p, which is x times y. Now for step 4, notice our equation has two variables, x and y. We need to get it in terms of just one. We can use the information from the question x plus y equals 8 to do this. By rearranging the constraint equation, we find that y is equal to 8 minus x. Now we can substitute this expression for y into our product equation. This gives us p as a function of x. Let's expand this to make it easier to differentiate. The product p is now 8x minus x squared. We have successfully created a single variable function to optimize. Now for step 5, we differentiate our function p with respect to x. The derivative of 8x is 8, and the derivative of negative x squared is negative 2a. So, the first derivative, p prime of x, is 8 minus 2x. In step 6, to find the turning point, we set the first derivative equal to 0. 8 minus 2x equals 0. Solving for x, we add 2x to both sides to get 8 equals 2x, and then divide by 2 to find that x equals 4. This gives us one possible value for x. Now we use our original constraint to find y. If x is 4, then y is 8 minus 4, which is also 4. We should use step 7, the second derivative test, to confirm this is a maximum. The first derivative was 8 minus 2x. The second derivative, p double prime of x, is just negative 2. Since the second derivative, negative 2, is a negative number, it's less than 0. This confirms that at x equals 4, we have a maximum value. So for the product to be a maximum, both integers must be 4. Let's quickly verify our answer using the provided memo. The memo also states the numbers are 4 and 4. Verified. Let's move on to our next example. By the end of this scene, you'll be able to find two numbers whose sum is a constant and whose sum of cubes is a minimum. Example 3.7 asks us to find two numbers, x and y, that add up to 25, and their sum of cubes, x cubed plus y cubed, is a minimum. We'll follow the same optimization strategy. First, the objective. We want to minimize the function s, where s is x cubed plus y cubed. Our constraint is that the sum of x and y must be 25. Next, we express s in terms of a single variable. We can rewrite our constraint to solve for y equals 25 minus x. Then we substitute this into our objective function for s. So s is equal to x cubed plus the quantity 25 minus x cubed. Now we differentiate. Using the power rule and chain rule, the derivative ds odd dx is 3x squared minus 3 times the quantity 25 minus x squared. To find the minimum, we set this derivative to 0. This gives us 3x squared minus 3 times the quantity 25 minus x squared equals 0. We can divide by 3 and rearrange to find that x squared equals 25 minus x squared. Taking the square root of both sides gives us two possibilities. Let's solve the first one. X equals 25 minus x. Adding x to both sides gives 2x equals 25, so x equals 12. The other case, x equals negative 25 minus x, would give 2x equals negative 25. Squaring a negative number would result in a positive, so this case is valid. Let's confirm using the second derivative test, just to be sure. It's good practice. We can expand the first derivative to make the second derivative easier. ds dx simplifies to 150x minus 1870. Differentiating this, we find the second derivative, d squared s over dx squared, is simply 150. Since 150 is a positive number, this confirms we have found a minimum at x equals 12.5. Finally, we find y equals 25 minus 12.5, which is also 12.5. So the two numbers are 12.5 and 12.5. This seems to be a common pattern with these types of problems, where the values are equal. Let's check our memo. Yes, the solution confirms x is 12.5, verified. Now let's tackle a more geometric problem. In this scene, you will learn to maximize the area of a right-angled triangle given a constraint on its side lengths. Example 3.8 states that the sum of the two shorter sides, or the legs, of a right-angled triangle is 15 centimeters. Our goal is to find the lengths of these sides that result in the largest possible area. Let's start with a sketch to visualize the problem. We have a right-angled triangle. Let's call the horizontal side x and the vertical side y. Step 3, the objective is to maximize the area of the triangle. The formula for the area A is 1/2 times the base, x, times the height, y. For step 4, we need to reduce the variables. The problem tells us the sum of the two sides is 15. So, our constraint is x plus y equals 15. We can solve this for y, which gives y equals 15 minus x. Now we substitute this into our area formula. Expanding this, we get a equals 1/2 times 15x minus x squared. We have a function for area in terms of a single variable, x. Step 5. Differentiate with respect to x. A prime of x is 1/2 times the quantity 15 minus 2x. Step 6 is to set this derivative to 0. This gives us 15 minus 2x equals 0. Solving for x, we find that x equals 15 over 2, or 7.5. Now we find the corresponding value for y using our constraint. Y equals 15 minus 7.5, which is also 7.5. Just for practice, let's use the second derivative test, step 7, to confirm this is a maximum. The first derivative, a prime of x, was 1/2 times 15 minus 2x. The second derivative, a double prime of x, is 1/2 times negative 2, which is negative 1. Since the second derivative, negative 1, is less than 0, we have confirmed that x equals 7.5 gives a maximum area. Therefore, the sides of the right-angled triangle that maximize the area are both 7.5 centimeters long. Let's check the memo. It says the sides are 7.5 centimeters and 7.5 centimeters verified. This next example presents a more complex challenge. By the end of this scene, you will be able to maximize the area of a right-angled triangle where the sum of a leg and the hypotenuse is fixed, and you'll see a clever alternative solution. In example 3.9, the sum of a side and the hypotenuse of a right-angled triangle is 15 centimeters. We need to find the lengths of these two sides and the angle between them for the area to be at its maximum. Let's sketch this triangle. Let the vertical side be x, the horizontal side be z, and the hypotenuse be y. The angle between the side x and the hypotenuse y is theta. From the sketch, we have two key equations. The area, our objective, is 1/2 times base times height, which is 1/2 x is z. The Pythagorean theorem gives us our constraint. X squared plus z squared equals y squared. Now, the hard part. We need to write area A using only one variable. This requires a few substitutions. First, from the hypotenuse constraint, we can express z squared as y squared minus x squared. Then, using our main constraint that x plus y equals 15, we solve for y, getting y equals 15 minus x. Substitute e back into our expression for z squared, expand and simplify, and we find that z squared equals 225 minus 30x. This means z is the square root of 225 minus 30x. Finally, we substitute this expression for z into our area formula. This gives us a equals 1/2 x times the square root of 225 minus 30x. This function is a bit complicated, and differentiating it would require the product rule and chain rule, which is long and prone to errors. Here's a clever trick. If a number is positive, maximizing that number is the same as maximizing its square. Since area must be positive, we can work with area squared, which we'll call a squared. A squared is 1/4 times x squared z squared. Remember we found z squared was 225 minus 30x? Let's substitute that in. This simplifies to a squared equals 1/4 times 225x squared minus 30x cubed. This is a simple polynomial much easier to differentiate. The derivative of a squared is 1/4 times 450x minus 90x squared. Setting this to 0, we can factor out 90x. This gives us two solutions, x equals 0 or x equals 5. Since x is the side of a triangle, it must be positive. So x equals 5 is our only valid solution. Now we can find y is 15 minus x, so y equals 10. The question also asked for the angle theta. We can find this using cosine. Cosine of theta is the adjacent side, x, over the hypotenuse, y. That's 5 over 10, or 1/2. The angle whose cosine is 1/2 is 60 degrees, or pi over 3 radians. So, for the area to be a maximum, the side x must be 5 centimeters, the hypotenuse y must be 10 centimeters, and the angle between them must be 60 degrees. Let's verify with the memo. The values match. Verified. Our next example involves inscribed shapes. By the end of this scene, you will be able to maximize the area of a rectangle inscribed in a circle. We need to find the area of the largest rectangle that can be drawn inside a circle, given that the circle has a radius of 15 centimeters. The word largest tells us we need to maximize something, in this case, the area. Let's make a diagram. Draw a circle with a rectangle inside it. Let the width of the rectangle be x and the height be y. There's a crucial geometric property here. The diagonal of a rectangle inscribed in a circle is always a diameter of that circle. Our radius is 15 centimeters, so the diameter is 30 centimeters. This means the diagonal of our rectangle is 30 centimeters. We can now use the Pythagorean theorem on the rectangle's sides and diagonal. This gives us a constraint. X squared plus y squared equals 30 squared, which is 900. Our objective is to maximize the area A, where A equals x times y. We have our equations. Similar to the last example, we can use the trick of maximizing a squared to avoid messy differentiation. A squared equals x squared y squared. From our constraint, y squared equals 900 minus x squared. Substituting this in gives a squared equals x squared times the quantity 900 minus x squared, which simplifies to 900x squared minus x to the fourth. Now we differentiate this polynomial with respect to x. The derivative, dA squared over dx, is 1800x minus 4x cubed. Step 6 is to set this to 0. Factoring out 4x, we get 4x times the quantity 450 minus x squared equals 0. This gives us three possible solutions. X equals 0, x equals the square root of 450, or x equals negative square root of 450. We can immediately ignore x equals 0 and the negative value, as a side length must be positive. So x equals the square root of 450 is our answer. To simplify this, we can write it as 15 times the square root of 2. Now we find y is the square root of 900 minus x squared. That's the square root of 900 minus 450, which is the square root of 450. So y is also the 15 times the square root of 2. It turns out the rectangle with the largest area is a square. The question asks for the maximum area. Area equals x times y. This gives us 15 times root 2 times 15 times root 2, which equals 225 times 2, or 450 square centimeters. Let's check the memo. It also states 450 square centimeters. Verified. Let's look at the second part of the same example, which is a classic application of this technique. You will now be able to maximize the strength of a beam cut from a log. The second part of the question talks about the strength of a wooden beam, denoted by W. The problem states that this strength is directly proportional to the width, b, and the square of the length, l, of its rectangular cross-section. So W equals k times l times b squared, where k is some constant. A beam cut from a log means its rectangular cross-section is inscribed in a circle, which is the cross-section of the log. So, we're back to the inscribed rectangle problem. Our constraint is still the Pythagorean theorem. L squared plus b squared equals the diameter squared, which is 30 squared, or 900. Our objective is to maximize W. Notice the W equation already has b squared in it. This is convenient. From the constraint, we can solve for b squared. B squared equals 900 minus L squared. We substitute this into our strength formula. This gives W. W equals K times L times the quantity 900 minus L squared. Expanding this, W equals K times the quantity 900 L minus L cubed. This is a simple polynomial in L. Now we differentiate W with respect to L. Since K is just a constant, it carries through. The derivative, dW over dL, is K times the quantity 900 minus 3L squared. We set this to 0 to find the maximum. This means 900 minus 3L squared must be 0. Rearranging, we get 3L squared equals 900, so L squared equals 300. Taking the square root, we find the length L should be the square root of 300, which simplifies to 10 times the square root of 3 centimeters. Remember, length must be positive. Next, we find the width b using our constraint. B squared is 900 minus 300, which is 600. So b is the square root of 100, or 10 times the square root of 6 centimeters. Let's confirm this is a maximum. The second derivative, d squared w over dl squared, is the derivative of k times 900 minus 3l squared, which is k times negative 6l. At our calculated length, this second derivative is negative, which means we have found a maximum strength. The dimensions for maximum strength are L equals 10 times root, 3 and b equals 10 times root 6. Let's check the memo. The dimensions match. Verified. Our next problem involves geometry and volume. By the end of this scene, you will be able to maximize the volume of an open-top box made from a square sheet of metal. In example 311, we have a square sheet of metal with side length A. We need to cut identical squares from each corner and fold up the sides to form an open-top box. The question asks for the side length of the squares we should cut out to make the box with the largest possible volume. Let's visualize this process with a diagram. Let the side length of the small squares we cut from each corner be x. When we cut out x from each side, the side length of the base of our box will be the original side, qui was a minus 2 times qui size x. Now imagine folding up the sides. The base of the box will be a square with side length a minus 2x, and the height of the box will be the side length of the cutout squares, x. The objective is to maximize the volume of this box. The formula for the volume V of a box is length times width times height. In our case, that's a minus 2x times a minus 2x times x. This gives us our single variable function to optimize. The independent variable is x, the side of the cutout square. For step 5, we need to differentiate v with respect to x. We can use the product rule here. The derivative of the first part, a minus 2x squared, is 2 times a minus 2x times 2. The second part is just 1. This gives us dv over dx equals negative 4x times the quantity a minus 2x plus the quantity a minus 2x squared. Now we set this derivative to 0 for the maximum. Here's a clever way to solve this. Instead of expanding, we can see that a minus 2x is a common factor. Let's factor it out. This leaves us with a minus 2x times a minus 6x equals 0. This gives us two possible solutions for x equals a over 2 or x equals a over 6. We must consider the context of the problem. If x, the side of the cutout square, is a over 2, then we would be cutting out a square whose side is half the original sheet's side. This means we'd be cutting away the entire width of the sheet, and we'd be left with nothing to fold up. No box would be possible. Therefore, the solution x equals a over 6 is the only physically possible answer for maximizing the volume. Let's check our memo. It also concludes that x must be a over 6, verified. Let's work through a practical problem involving cost and area. By the end of this scene, you will be able to maximize a fenced area given a budget constraint with varying costs. Example 3.12 describes a rectangular area to be fenced near a farm stall. The key detail is the cost. One side of length x costs R250 per meter, while the other three sides, the other x side and both y sides, cost R150 per meter. We have a total budget of R5,000 and want to find the maximum possible area. This problem combines a cost constraint with an area objective. Let's draw the rectangle and label the sides x and y. The bottom side, which we'll call the premium side, has the higher cost. The area, A, that we want to maximize is x times y. Our constraint is the total budget. Let's calculate the cost of each side. The top and bottom sides are both length x. The bottom costs R250x and the top costs R150x. The two vertical sides are both length y, and each costs R150e. The total cost is the sum of all these. 400x plus 300 must equal 5,000. To get our area function in one variable, we need to solve the cost equation for either x or y. Let's solve for y equals 5,000 minus 400x all over 300. We can simplify this by dividing by 100, which gives 50 minus 4x over 3. Now we substitute this expression for y into our area formula. A equals x times the quantity 50 minus 4x over 3. To make it easier, we can pull out the 1/3. Area is 1/3 times the quantity 50x minus 4x squared. This is our single variable function to differentiate. The derivative is 1/3 times the quantity 50 minus 8x. Setting this to 0, we get 50 minus 8x equals 0, which means 8x equals 50. Solving for x, we find x equals 50 over 8 or 6.25 meters. Now we find the corresponding y value by substituting x back into our expression for y. This gives y equals 25 over 3, or approximately 8.33 meters. The question asks for the maximum area, so we multiply these dimensions together. The maximum area is x times y, which is 50 over 8 times 25 over 3. This calculates to 1250 over 24, or approximately 52.08 square meters. A quick check of the memo shows the same result. Verified. This problem highlights how you can use differentiation to solve real-world budget and resource allocation problems. Our next example involves finding the closest distance between a point and a curve. In this scene, you will learn to use optimization to solve this type of distance problem. Example 3.13 asks us to find the point on the curve y squared equals 4x that is closest to the point A with coordinates 2, 8. The phrase closest means we need to find the minimum distance. Let's draw a graph to understand the situation. We have a parabola y squared equals 4x, which opens to the right. We also have a point A at 2, 8. We need to find a point B on the parabola. Let's call it xy, such that the distance between A and B is as small as possible. To find the distance, we use the distance formula. Let's call the distance AB, and it's the square root of the change in x squared plus the change in y squared. A common trick with distance problems is that the distance will be a minimum when its square is a minimum. This avoids dealing with the messy square root in our differentiation. So we'll minimize the square of the distance, d squared, which is x minus 2, squared plus y minus 8 squared. Step 4 is to express this in one variable. Our constraint is the curve's equation, y squared equals 4x. We can substitute 2 times root x for y into our distance squared equation. Expanding and simplifying this, we get d squared equals x squared minus 32 times root x plus 68. We're now ready to differentiate this with respect to x. The derivative is 2x minus 32 times the derivative of root x. Setting this to 0, we get 2x minus 16 over root x equals 0. We can simplify this to x equals 8 over root x. Multiplying by root x, we find that x times root x equals 8. This is the same as x to the power of 3/2 equals 8. To solve for x, we raise both sides to the power of 2/3. This gives us x equals 8 to the 2/3 power. The cube root of 8 is 2, and 2 squared is 4. So x equals 4. Now we find the y-coordinate using our constraint. Y equals 2 times root x, which is 2 times root 4 or 4. So the point on the parabola y squared equals 4x that is closest to 2, 8, is the point 4, 4. The memo confirms this result. Verified. Our next example involves 2 optimization problems for the same shape. By the end of this scene, you will be able to find the dimensions of a cylinder that minimize surface area for a fixed volume, and vice versa. We'll tackle both parts of example 3.14. Part 1 asks for the radius and height of an open-top cylinder that minimizes its surface area, given a fixed volume of 64 pi. First, the objective. An open cylinder has a bottom circle and a side. So its surface area, A, is pi r squared plus 2 prh. The constraint is the volume V, which is pi r squared h, and it must equal 64 pi. From the constraint, we can solve for hh equals 64 over r squared. We substitute this into our area formula, getting A equals pi r squared plus 2 pi r times 64 over r squared. This simplifies to pi r squared plus 128 pi over r. Now we differentiate A with respect to r. The derivative is 2 pi r minus 128 pi over r squared. Setting this to 0, we find 2 pi r equals 128 pi over r squared. Multiply both sides by r squared to get 2 pi r cubed equals 128 pi. Dividing by 2 pi gives r cubed equals 64. The cube root of 64 is 4, so r equals 4 centimeters. The question also asks for the height, h. We use our expression for h, which is 64 over r squared. 64 divided by 4 squared is 64 over 16, which is also 4 centimeters. So the minimum surface area occurs when the radius and height are equal. Let's quickly look at part 2. This time, the surface area is fixed at 150 pi, and we need to find the dimensions for the maximum volume. Here, the cylinder is closed, so its surface area formula includes 2 circles. The area, A, is 2 pi r squared plus 2 pi r h, and it equals 150 pi. The objective is to maximize the volume V, which is pi r squared h. First, simplify the constraint by dividing everything by 2 pi. This gives r squared plus rh equals 75. Now, solve for h to get h equals 75 minus r squared, all over r. Substitute this into the volume formula. After substituting and simplifying, we get V equals 75 pr minus pi r cubed. Differentiating this with respect to r gives dV over doctor equals 75 pi minus 3 pi r squared. Setting this to 0, we find that r squared equals 25, so r equals 5 centimeters. Finally, we find the height. H equals 75 minus 5 squared, all over 5, which is 50 over 5, or 10 centimeters. The memo confirms these values. Verified. Notice how the objective and constraint switch roles between the 2 parts, but the process remains the same. Our next example is another classic geometry optimization problem. In this scene, you will learn how to find the dimensions of the largest cylinder that can be inscribed inside a cone. Example 3.15 asks us to find the dimensions, that is, the radius and height, of the largest cylinder that can be fit inside a cone with a base radius of 14 centimeters and a height of 42 centimeters. The phrase largest cylinder means we need to maximize its volume. Let's begin with a sketch. We have a cone. Let's call the base radius of the cone r and its height h. Inside, we have an inscribed cylinder. Let's call the cylinder's radius r and its height h. The objective is to maximize the cylinder's volume, v, which is pr squared h. We need a relationship between r and h to express v in one variable. We can find this relationship using similar triangles. Look at a 2D cross-section of the cone and cylinder. We have a large triangle, let's call it ABC, representing the cone, and a smaller triangle, EFC, representing the top of the cylinder. Because these triangles are similar, the ratio of their corresponding sides is equal. The side AB, cone height h, is to EF cylinder height h, as BC, cone radius r, is to FC. Now FC is the cone's radius minus the cylinder's radius, so FC is 14 minus r. We have the proportion 42 over h equals 14 over 14 minus r. Cross-multiplying gives 14h equals 42 times 14 minus r. Dividing by 14 gives us a simple expression for the cylinder's height. H equals 3 times the quantity, 14 minus r. This is our constraint, expressed in terms of r and h. Now substitute this into the volume formula. V equals pi r squared times 3 14 minus r. Expanding this, we get V equals 42 pi r squared minus 3 pi r cubed. We have our function to optimize. Differentiating with respect to r gives dv over dr equals 84 by pi r minus 9 pi r squared. Setting this to 0 and solving for r, we find r equals 28 over 3 centimeters. We can ignore the solution r equals 0 as it would mean no cylinder exists. We can confirm this is a maximum using the second derivative test. The second derivative is negative, so it is a maximum. Finally, we find the height h using our constraint equation. H equals 14 centimeters, so the largest cylinder has a radius of 28.3 centimeters and a height of 14 centimeters. The memo agrees. Verified. Our final major example is a very interesting geometric problem. In this scene, you will learn to find the dimensions of the largest cone that can be carved out of a sphere. Example 316 asks us to find the height of the largest cone that can be made from a spherical object, or log, with a radius of 9 centimeters. The phrase largest cone means we need to maximize its volume. First, the sketch. We have a sphere, which we can represent with a circle in a two-dimensional cross-section. The sphere has a radius of 9. Let's inscribe a cone inside it. Let the cone have a base radius r and a height h. The objective is to maximize the cone's volume, which is given by the formula 5 equals 1/3 pi r squared h. Now we need to find a constraint, a relationship between the cone's radius r and its height h, using the sphere's radius of 9. This is where the geometry is key. Look at the triangle formed by the sphere's center, a point on the cone's base, and the cone's apex. Let the sphere's center be O, the cone's apex be A, and a point on the cone's base be C. The line OC is a radius of the sphere, so it has length 9. The line BC is the radius of the cone, r. The line OB has length h minus 9. Applying the Pythagorean theorem to the right triangle OBC, we get r squared plus h minus 9 squared equals 9 squared. Expanding this, we get r squared plus h squared minus 18h plus 81 equals 81. We can cancel the 81s on both sides. Rearranging, we get r squared equals 18h minus h squared. This is our constraint, giving us r squared in terms of h. Now substitute this into our volume formula. V equals 1/3 pi times the quantity 18h minus h squared times h. Expanding this gives V equals 1/3 pi times 18h squared minus h cubed. This is our function to optimize. Differentiate V with respect to h. The derivative, dv over dh, is 1/3 pi times the quantity 36h minus 3h squared. Set this to 0. Dividing by 1/3 pi, we get 36h minus 3h squared equals 0. Factoring out 3h gives 3h times the quantity 12 minus h equals 0. This gives two solutions, h equals 0 or h equals 12. A height of 0 obviously doesn't form a cone, so the height must be 12 centimeters. We can use the second derivative test to confirm this is a maximum volume. The memo confirms the result. Verified. We've covered a wide range of optimization problems. Let's finish with a special case that helps us consolidate what we've learned. In this scene, you will see an example where finding the maximum value of a function can be done more easily by comparing points rather than using the second derivative. Example 317 asks us to find the maximum value of the rational function f of x equals x squared minus x plus 1 divided by x squared plus x plus 1. Let's follow our strategy, starting with differentiation. We need to find the derivative of this function, f prime of x. Since it's a fraction, we must use the quotient rule. Applying the quotient rule, we differentiate the numerator, multiply by the denominator, subtract the numerator times the derivative of the denominator, and put it all over the denominator squared. This is a very complex expression. Let's expand and simplify. After carefully expanding and simplifying the numerator, we find that a lot of terms cancel out. The numerator simplifies to 2x squared minus 2. The denominator is the quantity x squared plus x plus 1 squared. This simplified derivative is a relief, but notice that it was a lot of algebra. For a maximum or minimum, we set the derivative to 0. A fraction is 0 only if its numerator is 0, so 2x squared minus 2 equals 0. This leads to x squared equals 1, which means x equals plus 1 or x equals minus 1. These are our two turning points. Now, step 7, we need to decide which one gives the maximum. We could use the second derivative test, but the first derivative was already complex. Differentiating again would be even harder. The memo provides a great shortcut here. Just evaluate the original function f(x) at these 2 points. Let's test x equals 1. Plugging this in, we get 1 over 3. Now let's test x equals negative 1. Plugging this in, we get 3 over 1, which is 3. Comparing these values, we can clearly see that 3 is the larger value. Therefore, the maximum value of the function f(x) is 3. This shortcut saved us a lot of calculation and potential errors. The memo also states that the maximum value is 3. Verified. So, remember, sometimes the best way to determine the nature of a turning point is not the second derivative test, but a simple comparison of the function's value. Let's revisit our first problem from today's session. Example 319. Now that we've seen several different types of optimization problems, you should be able to approach this problem with a clear strategy. The problem asks for the time when the distance between Tom's father and Tom is a minimum, and what that minimum distance is. We have speeds of 4 and 5 kilometers per hour, and an angle of 60 degrees between their paths. The first step is to visualize this with a diagram and define our variables. Let's draw a triangle. Point B is Tom's home. Point A is the park. Point C is the friend's house. The distance BA is 4 kilometers. The angle at B is 60 degrees. Let's introduce a variable for time. Let it be the time in hours after they both start moving. The father starts at the park and walks towards home. After T hours, he has walked 4 kilometers. His remaining distance from home, at point P, is the total distance, 4 kilometers, minus the distance he walked, 4T. So PB is 4 minus 4T. Tom starts at home, B, and walks towards the friend's house. After T hours, he has walked 5T kilometers. His distance from home, at point Q, is 5T. The distance between them, PQ, is what we want to minimize. We now have a triangle PBQ. We know two sides. PB equals 4 minus 4T and BQ equals 5T, and the included angle 60 degrees. We can find the length of the third side, PQ, using the cosine rule. The cosine rule gives us PQ squared equals PB squared plus BQ squared minus 2 times PB times BQ times the cosine of 60 degrees. The cosine of 60 is 1/2. Now we substitute our expressions for PB and BQ into the rule and simplify. Expanding the squared terms and the product, and then combining like terms, we get the squared distance. PQ squared equals 61 squared minus 52T plus 16. This is a quadratic in T. The distance PQ will be a minimum when its square PQ squared is a minimum. We can now differentiate this expression. Step 6. Differentiate with respect to t. The derivative of pq squared is 122t minus 52. Setting this to 0, we solve for t. We find that t equals 52 over 122 hours. To get the answer in minutes, we multiply by 60. This gives us approximately 25.57 minutes. This answers the first part of the question. The minimum distance will occur after about 25.5 minutes. Now for the second part. What is that minimum distance? We substitute our value of t back into the expression for pq squared. We calculate the result and find that pq squared is approximately 4.918. To get the minimum distance pq, we take the square root of this value. The square root of 4.918 is approximately 2.218 kilometers. The memo confirms our answers for both parts. Verified. Let's quickly review the core ideas we've covered today. Optimization using derivatives is a powerful tool to find maximum and minimum values in a variety of situations. The process always follows the same logical steps. First, you must identify what quantity you need to maximize or minimize and represent it as a function. Second, you must find constraints that relate the variables in that function and use them to rewrite the function in terms of a single variable. Third, differentiate the function, set the derivative equal to 0, and solve. This gives you the critical points where a maximum or minimum might exist. Finally, use a test, like the second derivative test, to confirm which is which, and then calculate your final answer. This systematic approach allows us to solve complex problems with confidence. The most difficult step is often setting up the correct equations from the word problem. So practice drawing diagrams and identifying objectives and constraints. Thank you for joining this tutorial. You can find all the formulae used in these problems in Table 3.1 and 3.2 of the notes. If you found this video helpful and want to master more maths topics, please make sure to subscribe to our channel, Maths Zone African Motives. See you next time.